Nerede millet? Okay, so this is where we left off last time. We talked about linking and mounting and other types of system calls, like the changing the access modes of a file. In Unix we have such a system call. Does anybody know what this 0644 mean? chmod file 0644.
Can read but can't execute or write.
Say it again, louder.
It can read the file but it cannot execute it or write it.
So can you read it? Okay, good. So it means that, first of all, when it starts with a 0, it means it is octal. So this is a 6 in octal number. 6 is 0, 0, 1, 1. 4 is 0, 0, 1, and this 4 is 1, 0, 0. Read, write, execute. Okay, this is read, write, and execute. And 6 is the owner. This is the group, and 6 is the owner. Owner has the read, write privileges. Okay, so this read, write, execute. Okay, so owner has read and write privileges but no execution privileges. Everybody else, okay, has read privileges but no write or execute privileges, and this is the group one. If you belong to a group, this is your privileges. So this is just a specific notation for the Unix system, how you define the security for a file. In Windows we don't have this exactly. We have other ways of doing this, but again it depends from system. It changes from system to system. And again, as I said, there are many system calls and systems programming courses about learning this interface for Unix or Windows operating system. For Windows, we have similar system calls or procedure calls. Okay. Again, I like to make this distinction. Sometimes we use it interchangeably, but procedure calls are different from system calls. Sometimes an operating system, you will say that, do this for me, and the operating system does that without, in the libraries, without going to the kernel mode, and handles and returns the results back to you. That would be the most efficient. But most of the time, whatever you make a call, okay, it might be a kernel call, trap to the kernel and context switch and etc. So Windows says that, okay, I'm going to define these procedure calls. They may not be exactly necessarily system calls, okay, and these are the things. So Windows has, what did we say for the POSIX there? We have about 100 nicely nicely, okay, defined procedure calls for POSIX, but for Windows this number is more than 1,000. Okay, because Windows tries to achieve many things at the same time. For example, graphical user interfaces, handling of the graphical user interfaces is part of the Windows operating system. Okay, if you like to open a new window, move window from one position to another position, change the shape of the window, the operating system will help you in doing this kind of stuff. That's why the API of the Windows operating system is more complicated, more detailed than the POSIX API, POSIX standard. Okay, so and Windows makes that, okay. Sometimes a procedural call might be a system call. Sometimes it is not, and it is up to me when to make that call. And from one version of the Windows, it might be a procedure call. For other versions, it might be not a procedure call. So it is up to me. So you are not going to assume that some of them will result in system calls and some of them will result in not system calls. So why do we care? We care because if a procedure call makes a system call, then that procedure call is probably going to be expensive because that will require a context switch. If I know that a procedure call is not going to be a system call, then that's going to be fast. Probably I will handle it without going to the kernel mode, and it will come back very quick. That's why it might be important to know that, but Windows doesn't tell you that it's going to be a system call or not. Okay, so these are some of the examples for the Windows and the POSIX operating system. Can we see some of the differences, like here, like mounting and unmounting? Well, there are different versions of these two procedures in Windows, but not exactly the same thing, like the linking and unlinking it. Okay. What else? Yeah, this changing the mode of a file, or sending a kill is used for sending a signal to a running program, to a process, and the signal number 9 is the kill signal. Okay, but we call all of them are like kill signals. So signal number 9 is kill signal, and Control C sends that signal to the process, and the processes by default have to receive those signals and they have to handle it. Okay. Other than that, kill, there are other types of signals like the suspend signal, and what else? Refresh the other. I forgot the other signals. Again, maybe Erhan Hoca will tell you. Unix. Okay. Kill signals. What kind of signals do we have? Yeah, good. Okay. So this one is the 9. Quit, terminate. Okay, these are all terminate signals. There are other types of signals. Okay. Some of them are implemented by all the. Okay, so these are the possible signals. So number 9 is a kill signal. So how do I send a kill signal to a process? You will say, for example, let me wait until this thing. Okay. So when I say kill minus, okay, so this is the signal of it. When I say kill 8, I am killing my bash, process number 8. Okay, so that will take everything out. So let me start it again. What kind of other signals do we have? Okay, interrupt process stream. Control C is the same as Control C. Terminate. Okay, so signal continue. Okay, so this will signal stop. This will pause the process, and this will continue. So this will suspend it. 19, and the other one will continue it. Let's try to suspend. Okay, can we do that? So PS, my bash is 22, and I like to send, what was the number for suspend? 19 and 22. So my bash is suspended, so I cannot, I mean, since I am suspended, I mean the interactivity is no more. So I don't know. Okay, it came back. So somebody wake me up. Yeah. What did make? Okay, when I resize the window. No, this time it didn't happen. I don't know what happened. Control Z. No, since I lost the keyboard.
Then it is a bug in Windows substance volume.
What?
When you resize window.
I resized it. You see, I am resizing it. Maybe resize it through this. No, I don't know what happened a few minutes ago. So I am stuck here. So these are the things that are specific to Unix. In Windows, we don't have this kind of signal mechanism. Okay, and it is up to you to implement some of them. Some of them are implemented, some of them are not implemented. But usually, this is the most popular one: kill signal. Okay. So they say that when 15 doesn't work, do this one. I don't know. Just read it. Maybe Erhan Hoca will go over them. Okay, so I mean, this one doesn't exist in Windows. Doesn't mean that Windows is a less capable operating system. No, it has other ways of achieving this kind of stuff. Anyway, okay, let's move on. So now I am going to look at the structure of the operating system. We said that operating systems are large. If you consider the Windows operating system, we are talking about 100 million lines of code. That's that much. Okay. If you consider everything that comes with Windows, including all the drivers, including all the stuff. For example, the Paint, Windows Paint comes with Windows. Okay, right? All the file-related stuff and everything. It is very complicated. It is very large. And if you say that, well, most of it is not part of the kernel. If you think about the kernel, now we are talking about million lines of code, okay? Million lines of code is not a simple piece of software. It is complicated. So you need to structure it, okay? You need to have some kind of a structure for your operating system. How do you design your operating system's architecture so that it is modular, it is easy to maintain, it is easy to extend, and etc. But these are the types of the operating system, and unfortunately, the most common structure for the operating system is not structure much. We call these monolithic systems. Okay, there is only one program running. And this program is trying to do everything, including the process scheduling, memory virtualization, input-output management, and everything. So there is only one entry point. You make a system call, and it calls the system, and the system handles it. Well, I mean, so there is only one program. If this program crashes, everything crashes, right? So there is only one process running as the kernel. Well, there is one program doesn't mean that it doesn't have any sub procedures. Of course, we have modules, service procedures regarding the file management, file systems, memory utilization, CPU sharing, and CPU scheduling, and etc. But there is no constraint that this one can call this one can call this one can call this one. It is all free because they are all in the same address space. There are no constraints imposed, and these constraints are not enforced by the hardware. So that's the structure of the operating system, monolithic systems. That's the basic structure of it. Okay, so that's the Okay, the entire operating system runs as a single program in the kernel mode. It is efficient. You don't have to think about what am I going to do now, who's going to, what kind of module I am interact with. Everything is under your hands. Okay, you can call anybody, you can use anybody's service. But the thing is that if one of them fails, the whole operating system crashes. People realized this and they started building these kind of systems, layered systems, not monolithic. So the operating system has more than one mode, okay, and each mode is more privileged. For example, at the bottom, this processor allocation of multi-programming layer is a layer number 0 and it is most privileged, okay. If you are above this layer, then you have to make another system call. So operating system makes other levels of system calls. Okay, at the top you have the operator. Operator doesn't have much privilege. If it needs something, then it has to go to layer 4, then 3, then 2, then 2, then 1, then 0. Okay? So this means what? If I have a buggy input-output management module, okay, that buggy module cannot by accident create a CPU scheduling problem because it doesn't have any privilege to do so, okay? That input-output management can only modify input-output registers and etc. And the hardware most of the time, in the case of Multics, okay, hardware will enforce these layered structure, okay? So you design your operating system this way, and each layer knows their responsibility and hardware knows their responsibilities. If this layer, the memory and drum is for the secondary storage. If this layer tries to do something about CPU management, no, the hardware will tell the system that somebody is trying to do a process that is not valid for that layer. Okay, so these are the layer system. Of course, this is much better in terms of security system robustness, but what is the downside? What is the downside of each layer making a system call to the layer below? Yes?
Performance.
Efficiency, performance, exactly. I mean, remember what we said about the system calls? System calls are nice, but they are inefficient because you are switching context, right? So layer systems are like that. And Multics doesn't call them layer systems; it calls them rings. And Multics, the operating system, operating system and the hardware designed together, and they call them rings. And the hardware knows about the rings, and this is all enforced during the runtime everywhere. Okay, another way of organizing your operating system is this. Okay, we talked about the robustness of the operating system. If there is something wrong about the operating system's kernel, the whole machine crashes, and we are in a bad situation. We have to reboot the computer, right? The microkernel people say that if we keep the kernel very, very small, then there is a very small chance of, crashing the whole operating system. Why? Because only a few thousand lines of code will run in the kernel mode. If there are bugs in them, okay, having the probability of a bug in 10,000 lines of code is much smaller than having a bug in a kernel of size 1 million lines of code, right? So that's the idea of microkernel. Let's keep the kernel small. Well, using the small kernel, how are you going to do the disk management and the networking and the print server, file servers, etc.? They say that I am not going to do that, okay? All the disk management, terminal management, file systems, okay, reincarnation and etc., they are all will be in the user mode, okay? So these are regular C programs. Of course, they are not in the privileged mode. If this one says that I need to get this data from disk and move it to the other part, I am going to ask the kernel to do it for me. Okay? So most of the time, when these processes run in the user mode, they will keep asking the operating system to do stuff for them. So lots of system calls, lots of inefficiency, but only this part, since only this part is in the kernel mode, it is not possible to crash the kernel very easily. Your disk management module might crash, okay? Your networking module might crash, but that will not put you in a very bad situation because your whole operating system is running. In fact, there is this reincarnation module running. The responsibility of reincarnation module is run from time to time, check if file system is alive, its networking is alive, its print servers are alive. If they are alive, then that's fine. If they are not alive, then it just reinitializes them. It just creates a new process for those. Okay, so it is checking the system health all the time. Okay, other than the kernel, if anything goes down, this one will reincarnate them. So that's the idea of microkernels. People use this microkernel idea, this Minix 3. Okay, it's an operating system, experimental operating system by the author of this book, Tannenbaum. Okay, he started with Minix and Minix 2 and Minix 3. So it uses this idea. It says that I have only 12,000 lines of C code and 1,400 lines of assembly code for the kernel. So on the average, if you have a professional code, one bug per 1,000 lines is something expected. Okay, humans make mistake. I hope you realize this by this age of yours. Okay, humans make mistake, and this code is written by humans. So you expect one bug per 1,000 lines. So if I have 12,000 lines of code, you would expect that Minix has on the order of, we are talking about tens of bugs for the whole kernel. Okay, but if you are talking about Windows, there will be lots of bugs. The problem with Windows kind of operating system is that, remember the drivers? If I have a new device, for example, I got this nice USB camera, and I connect it to my system, and I need to install the driver for this USB camera to my system too. Driver is written by the producer of this camera. Okay, so you have to take the driver in your kernel mode. If the driver makes a mistake, the whole system crashes. It becomes the problem of the Windows. Well, Windows says that I didn't write that code. How am I responsible? But I mean, I keep Microsoft responsible for this because the Microsoft operating system crashes. This one says that, okay, no drivers will be part of the kernel. Okay, they will be outside. If they crash, that will only crash this USB device, not my operating system. Yes?
So does it more difficult to handle this kind of faults in kernel mode rather than the user mode? What's the difference? Fault is fault in both sides, I mean.
You are saying that you need to be more. I mean, you need to put more work. Yeah, I mean, of course it is the easiest one is this one to write, right? You don't have to be careful about anything. There are no rules. Everybody can call the other. So it is easy to write at the beginning. For this one, there are lots of rules. You can't do that, you can't do that, you can't do that, okay? So this is difficult, right? But when it comes to debugging, finding the bugs and that kind of stuff, of course, this is more advantageous, okay? So, I mean, 12,000 lines of code and rest of them is in the user mode doesn't mean that the whole operating system is simpler. Okay, this operating system is as complicated as the Windows operating system. Okay.
Is Windows monolithic?
Yeah, it started as a monolithic operating system, but later they used lots of ideas from the others. In the monolithic operating system, there is only one process, but obviously I showed you the number of processes that I am running. Most of them were parts of the Windows. Okay, so it is not running as a single process. Okay, so these are basic definitions or basic structure types of the operating systems. The modern operating system uses ideas from all of these kinds of structure types. You wouldn't say that Windows is this. For example, when I say Minix is this one, other than this, I cannot give any examples. Or I didn't give any examples of a monolithic operating system in this slide because there are no. How come the Minix can be a microkernel operating system? Because it is developed just to be an experimental operating system. Okay, it is not commercial. Nobody uses Minix for something useful other than the teaching purposes. Okay, Minix is designed to be a microkernel operating system. That's it. It is good for experimentation and teaching and learning. Okay, that's why I can give that Minix is a microkernel operating system. A slight variation of this one, microkernel operating system, is the client-server model. Okay, client-server model. So you would say that your operating system is in parts. There are many modules like the file server, process server, terminal server, networking server, and etc. Okay, each one is running on top of the kernel. It communicates with the kernel. So the idea is, why can't I run these modules on different machines? Right? Why can't I run these modules on different machines connected with a network? So that would make it even more robust. Why? If the machine goes down here, okay, let's say if there is a power outage, the machine goes down there, okay, maybe this is not a good example, but how about this one? If the machine goes down there, the terminal server is out, but main operating system like the file server and the process server still can continue, okay? Or I can just initiate another backup server from somewhere else, okay, over the campus and etc. This is called client-server model. Most of the time, these clients and servers they live on the same machine. Actually, they run on the same machine, but it is okay to separate them into different machines, and these are called distributed operating systems. If you put them in different physical machines connected by a network, distributed operating systems, again, they are much more robust against software-related crashes, also hardware-related crashes too. Okay, so this is the client-server model. Another structuring mechanism comes from the virtual machines. Virtual machines are very interesting, and people have realized this in 1960s, and we have been using these virtual machines a lot. Okay, so in the virtual machine, IBM initiated this model actually in 1960s, as I said before. Let's say I have this 370 bare hardware. This is 370 machine. This is our hardware, okay. And IBM realized that if I run many operating systems, the copies of the same operating system, CMS is the operating system. If I run many operating systems on the same machine, if one of them crashes, the others will continue running. So why don't I do that? So they put this VM370 layer, software layer, okay, on top of the hardware. The task of this VM370 is to show many different hardwares, okay, to the upper levels. This operating system here thinks that it owns a IBM 370 hardware, and this one too. So as a regular program, when I run at this point as a regular program, when I make a system call, this one gets it. It is a code by this operating system, and it makes another system call to the VM370, and VM370 handles it and puts the results back in. So this is a very simple layer of hardware. Okay, it takes requests from the upper layer, it handles them, it gives them back, and it does some scheduling, some memory management. But the more complicated parts of more detailed parts of the operating systems are handled by this one, and that one. So these are called virtual machines. Okay. And again, this one doesn't know that it is running on a software system. This one doesn't know that it is running on a software system. It thinks that it is running on the bare hardware, and it thinks that it is the only operating system that owns that bare hardware. Okay, so this layer fools them into thinking that they have the whole machine. So this is a very nice way of structuring your operating systems. And if one of them crashes due to some software issue, the others will continue. It is very easy to add more operating systems on top of it. Make this 5, 6, 7 whenever it is needed. It is very easy to take backups of them. It is very easy to give a smaller chance of using the CPU for this one. So less privilege for this one, more privilege to that one. And let's say if I am a service provider, okay, I told you that I am going to handle your emails, and I am going to handle the other company's emails, and I am going to handle the other company's emails, okay. If one of the, thank you. Did everybody sign this? Everybody? During the break, okay. So if one of the companies are receiving lots of emails, then I can maybe make that, maybe increase the priority of that operating system a little bit more, so I can handle these kind of dynamic variations of the request and that kind of stuff. Okay, virtual machines are nice, and we are using them a lot in today's world. Okay, so as I said before, this was again invented in 1960s. And IBM has designed their hardware to make this virtualization available for everybody. But for the PC world, again, we couldn't do the virtualization because hardware was not good enough, strong enough. Because for the virtualization to work, I need to get some support from the hardware, and that support were not there until 2000s and maybe 2005. After that, virtualization became feasible on PCs too, and nowadays we use virtualization a lot. There are two types of virtualization. We are going to look at them in a separate chapter, but let's look at them now. Okay. One is this one, type 1 hypervisor. Sometimes operating systems are defined as supervisors, like the boss, like the manager, supervisor of all the processes, etc. Okay, this Windows operating system works and it supervises all these processes. But if you put one more layer of management, this one becomes hypervisor, not supervisor, but hypervisor. Okay, so this one is type 1 hypervisor. This type 1 hypervisor is same as IBM's solution here. Okay, it runs on bare hardware, and you can install many operating systems on top of type 1 hypervisor. It is the responsibility of the type 1 hypervisor. Okay, for example, this Windows operating system, it is trying to, let's say, modify input-output register, which is a privileged instruction, right? So it causes a trap into this type 1 hypervisor. And in fact, we are running Windows here in user mode. Okay, only this one works in kernel mode. Okay, this one, they all run in user mode, but the Windows doesn't know that it is running in user mode. It thinks that it has privilege to change the I/O registers every time it needs, but whenever Windows makes a change in the I/O register, okay, it causes a trap. Hardware causes it, and that trap is handled by the hypervisor. Okay, that's what I am talking about. The hardware help. Hardware has needs to way of handling these kind of privileged instructions, causing the proper trap, and hypervisor will handle it. Okay, so The hypervisor knows how many operating systems are running, and it does the scheduling and the memory management. And again, this is not a very complicated stuff, this part, and it is used a lot. This is type 1 hypervisor. Type 2 hypervisor is different. Type 2 hypervisor, okay, again, it's a hypervisor, but it runs like a regular. It runs like a regular process on top of a host operating system. Let's say this is my Windows. Okay, on top of Windows, I am running this process. This process shows itself as like a hardware layer, and you can install Windows on top of it, or Linux, or some other operating system. And this operating thinks that it is running on bare hardware, but it is running on top of a hypervisor, type 2 hypervisor. So it is the task of the type 2 hypervisor to get the guest operating systems requests and translate them into the host operating system's requests. Okay. Again, obviously, this is a special process. It needs to use some of the CPU's virtualization features. So you install this process as a special process. You give it some privileges. Otherwise, it wouldn't work. Okay? So, again, we are talking about this because these are different types of operating system structures, architectures. Okay? Sometimes you design your operating system knowing that it is going to work like this. It's going to work like this. Good. Any questions? Yes.
Your Ubuntu is type 2 hypervisor?
Kind of. Well, this is not a perfect example of Ubuntu. This is just an emulation. Okay. Since this is an emulation, I cannot get everything that I get from a regular Ubuntu system. And Windows provides it, and it is similar to type 2 hypervisors. And Windows kind of is becoming more and more like a Ubuntu or Linux operating system company. They say that in a few years we are going to run Ubuntu or Linux instead of Windows. And they say that they have this submodule, Linux subsystem module, they call this, and it runs like this type 2 hypervisor. Well, they did this for a long time, maybe for 5-6 years they have been doing this. But every time they make a new edition, this gets more and more efficient. This gets more and more Unix-like environment. I think in the next release of Windows, we are going to see a perfectly running Ubuntu system on top of Windows. And you won't be able to see the notice. Yes. Yeah.
Actually, in new versions, it uses real Linux security.
Yeah, it is. So it is more like this one. Real Linux kernel is running on top of something, and at the bottom there is Windows. Okay. Well, it is. I mean, it takes some hardware. It takes some resources. It is a little bit inefficient, but again, we'll have a separate chapter, and we will talk about this. Surprising thing is that sometimes if you run guest operating system on top of this kind of hypervisors, okay, it turns out that it is faster than the original guest operating system running on the bare hardware, because of the context switch time, really. Okay, because they are all running in the user mode. Okay, since they are all running in the user mode, if you take advantage of it, that's going to be faster. So this is not generalizable, but if you are smart enough, you will take advantage of it. So inefficiencies goes away. Yeah.
When guest operating system creates a trap and sends it to the type 2 hypervisor.
You are talking about this one?
Yeah, type 2 hypervisor.
Okay.
Type 2
Operating system produces a trap. Yeah. This one handles it.
Type 2 hypervisor directly pass it to the bare hardware or the host operating system?
Well, this one says that translated to the host operating system requirements, host operating system system calls, and this one will handle it. Sometimes you do this. You put a little hole in there. This will talk to directly hardware. Sometimes do that too. That's why if you install these kind of hypervisors, VxWorks and etc. If you install this kind of hypervisor, you need to install lots of stuff to Windows, change lots of modification, etc. But the idea is to use this host operating system procedures. That's why these type of hypervisors are more complicated than that one, because this one needs to know both this one and that one very well. Okay, good. Let's move on. I'm not going to talk about Java Virtual Machine. Java Virtual Machine is something similar to those, but you already know that. Exokernel is another type of operating system structuring, and well, they try to address actually this sharing of resources between many different operating systems, and they made this sharing a lot easier. They say that, okay, this part of the memory is the virtual number one, this part of the disk is virtual number two, so this translation comes free. I mean, which one is using which, so scheduling is very, very easy. It talks about that one, exokernel. So I will skip this one too because we are running kind of late. With the operating systems are written in C and assembly. Of course, you like to write them more in C than assembly, but sometimes, for example, in C, there is no way to modify your stack pointer, okay? You cannot say stack pointer register, you cannot say in C, add 2 to the stack pointer, remove 2, subtract 2 from the such and such pointer, etc. register. You need to use assembly for those. For the places where you can use C programming language, of course you try to use C, okay? That's what we do. Luckily, most of the time C would be enough. For example, whole file system or process scheduling, most of it, or the memory management will be done in C. That means what? If you have the source code for your operating system, especially for the drivers and the upper layers procedures, you can use the same thing you can use the same source code for the other types of operating system. You just take the code and recompile for the other type of operating system. It just works, okay? So that's the advantage of having a high-level language like C. All you need is a compiler. Okay, so we know these. Okay, this is how the C programs work. Okay, we have the header files. Okay, we have the C source codes. We pass them through a preprocessor. So preprocessor does that. It handles all the includes and the defines and everything. So this one will produce a C file. Okay, with the C file, I can compile them. I make them into object files, and then I link them with my libraries, and this will produce me an executable program, right? That executable program is either the program running on top of an operating system, or this is our kernel. Okay, it might be our kernel. So who initializes the kernel? Of course, whatever starts the computer. Most of the time, it is our BIOS, right? BIOS will take this kernel and it will start the kernel, and the kernel becomes the operating system of our machine. So that's the chapter number 1. At the end of the chapter number 1, usually, I mean, this book says that operating systems are like circus, okay, like this. There are many things that are happening. Overall, it is fun, but things may get ugly, okay. From time to time, it is very dangerous. Everything has to be synchronized, everything has to be carefully organized, and etc. And that's why it is making fun of it. The other book, the other book by I forgot the name of the guy. It's called the Dinosaur Book. This is a circus book, or the other one is the Dinosaur Book. That one talks mostly about the history of the operating system, dinosaur operating systems, old operating systems, because they are the most relevant. So there is the circus book and the Dinosaur Book, 2 main operating system textbooks. So I don't know why I put it in there, but I think it was part of the slides. Okay, so we are going to talk about most of the stuff. Dining philosophers, process scheduler, server client. We talked about that. Okay, critical region. Yeah, we talked about thread, Linux and Unix. Okay, this is not bicycle but unicycle. Okay, these are the windows. Well, silly stuff. So if there are no questions, then I will start my chapter number 2, which is about processes. Chapter number 3 will be about memory. 4 will be about file systems. 5 will be about input and output. Okay. So let's start with processes. Yesterday I was trying to initiate this mode. Now I don't want it. So how am I gonna go back? I think it is somewhere view. Yeah. Not double page, but single page, not continuous, single page. Why did they make it so difficult to access this? Okay, good. So why didn't, so should I reload it again? Yeah, this one. Just get rid of it. Discard changes and load it again. Okay, good. So processes and threads. We are going to spend a lot of time on this chapter, chapter number 2. Maybe this is the most important concept about operating system, processes and then thread. This is how what was the, okay, two main things about operating systems, as you know. Abstract the details, hide the details of the underlying hardware. Okay, so we are going to hide the details of the CPU and resource management. Manage the resource of the CPU. That's what we are going to do. To do that, we need two main concepts. One of them is the processes. Related to processes, we have the threads. So we will keep talking about processes and threads in this chapter. Okay. My annotations, let me clear them. Okay. So we made this definition before. A process is simply abstraction of a running program. Okay, a running program, it has its memory, it has its address space, it has all the registers for it. So if you put them together and if you think them as a complete concept, we call that concept a process. And this idea of process is the one of the oldest. Okay, people try to conceptualize this at the beginning of the computing days, 1950s. Okay, it is oldest, but it is the most important abstractions, one of the most important ones. Okay, and since day one, we wanted to load more than one program at the same time in my memory. The idea was if one of the programs is blocked, I can continue running the other one. So in a pseudo way, maybe concurrent programming operation. Okay, so we try to turn a single CPU into multiple virtual CPUs. Okay, without the idea of process abstraction, we couldn't do that. That's why we say that the processes are the basic building blocks of the modern computing, and it's going to go that way. until we hit the days of the quantum computing. When the quantum computing comes, I think it's going to come, we might have some small slight changes to the idea of the process, because with the quantum computing, you do many things at the same time, sometimes infinitely many things at the same time. It doesn't fit the idea of the process much, so we need to make some changes. But until then, while we are using these von Neumann machines, the processor will be with us. Okay, so what did I say? Okay, we have a single CPU, just one CPU, but we have 3 processes loaded in this case on our machine, and we have the operating system too. Never forget that operating system is a piece of software. Okay, it has to use the CPU, it has to use the memory. Okay, while process number 1 is using the CPU, it owns the CPU, it does whatever it wants, unless it doesn't execute any out of privilege instruction, illegal instruction. Okay, so if it behaves nicely, it will keep using the CPU, it will keep using its own memory, and etc. When the time is up, okay, I need to switch from process number 1 to 2 or 3, or in this case, OS took the CPU. It probably has something to do. Maybe it is trying to, for example, an interrupt has occurred, an interrupt comes from the hard disk. Hard disk says that the data that you ask me is ready. It is just 2 megabytes of data. Take it. Operating system will take that data, put it in a suitable place in the memory, and it will inform whoever asks for that data. So sometimes the operating system uses the CPU. After it is done, it just schedules one of the processes to take the CPU again. Process number 2 take it, then process number 1, then process number 3, and it goes that way. But it doesn't. We don't show it that way, but switching from one process to other process doesn't happen like that. It is always operating system makes the decision. Okay, you don't directly switch from process number 1 to process number 2. Let's look at this picture here. Okay, at this point, okay, process 1 is using the CPU. Something has happened, and process 3 is using the CPU. Can you tell me what is happening here? When I say something has happened, many things can happen. What kind of things can happen so that process 1 stops using the CPU? It could be that I'm going to start talking about. It could be a timer interrupt, right? Remember the timer interrupts, which happens 30, 40, or 50 times a second. Okay, it happens, and timer interrupt has happened. So who's going to handle the interrupt? If it's an interrupt, operating system is going to handle it. And operating system said that, okay, timer interrupt happened, so what am I going to do? It has many things to do during the timer interrupts regarding the page tables and the file input, output, and that kind of stuff. We will see them later. And then CPU says that, okay, I am going to let the one of the processes run the CPU, but it looks like process 1 is out of time. It used the CPU more than enough. So out of this process 2 and 3, okay, it looks like I never let the process 3 use the CPU before, so I am going to let process 3 use the CPU. So that's what the operating system does. So timer interrupt is one. Tell me what other things can cause this kind of transition to the operating system. Timer interrupt.
Cache management.
What?
Cache managing.
What do you mean cache management? Cache management cannot happen
The process
while
uses cache, and when we change it, we need to remove old ones and.
Yeah, very good, very good. Well, usually the thing is this, cache management is done by hardware. Usually cache management is done by hardware. If you have a cache mess, okay, whatever you are loading to the cache from the main memory, okay, it is all managed by the hardware, and operating system doesn't know about it. It's because it has to be done fast. That's why you learn about the cache management in your hardware courses. In this book, there is no chapter, there is no topic about handling the cache. But we have something similar. We have the virtual memory management. Similar stuff happens there. Okay. What did I say? I cannot fit all of my programs in my main memory. Some of them has to be on the disk. If this process wants to access some memory location, not in the memory but on the disk, then that page has to be loaded. That's called page mess, like the cache mess. It's called the page mess. So page that has to be loaded from the disk, and operating system handles it. Yeah. So related to what you are saying, yeah, there might be a page mess fault or the interrupt, and operating system has to. It looks like all the hardware interrupts, like the page mess, timer interrupt, or hard disk interrupt. Hard disk said that something is ready, or keyboard says that somebody pressed the keyboard button. Take this button information from me. Okay. Or network card received a package. Say that I received a package, so what am I going to do with this package? Take it away from me. Okay. So they all cause an interrupt, and interrupts is handled by the operating system. Other than those hardware-related interrupts, what could happen so that there is a switch from process 1 to process 3? Yes?
So there is only one timer interrupt mechanism, right? Not all of the processes has its own timer interrupt.
Well, there is a device. There is a device named timer. Okay, it's an I/O. We call that an I/O device. It's not an I/O device, but let's say it's an I/O device. It is connected to the system bus. Okay, it causes timer interrupts, and you can program it as an operating system. I programmed it to cause timer interrupts 30 times a second. But also as a process, when I say sleep 100, what does that mean? It means I am going to block me for 100 milliseconds. Okay? After 100 milliseconds, cause an interrupt. Okay? That will tell the CPU that I am ready to run again. So you can program the timer like this too.
So in default, there is only one value, right? For example, 100 milliseconds. Every 100 milliseconds, there would be
No, this one will, well, I mean,
there would be
with the timer interrupt, yes. Yeah, every 100 milliseconds, the operating system wakes up. But for this one, as a process myself, okay, I am going to only cause one timer here. Okay, so that's. But here it cannot happen because, what? I mean, I am still running, right? I am not sleeping. I am running, and I am causing a trap to the operating system. What could happen, other than the interrupts? Yes.
Process 1 wants to activate process 2.
Process 1 wants to do what?
Run process 2.
With the process 2, can you explain that? Is that what you said?
Like parent process. Process 1 is parent process and wants to activate the process 3.
Okay, so if process 1 is trying to communicate with process 3 or trying to do something about other processes, that's what you are saying. Well, maybe we can generalize it and we can say that process 1 wants to do something related to hardware or the other things that it cannot do directly. So process 1 is maybe doing a system call. Okay, process 1 says that print this character on the screen. Process 1 says that load this data from the network. So this might be a system call too. Okay, there is no interrupt, but system calls. System calls are sometimes called software interrupts. Okay, not hardware interrupts. So process 1 itself is causing an interrupt, software interrupt. For example, sleep 100. It has to be handled by the operating system. This will cause a system call. Okay. And the operating system will handle it. It will program the timer for me for 100 milliseconds, and it will put me on the ready queue. I cannot run. No, it will put me on the blocked queue. I cannot run because I need to wait 100 milliseconds, and it is going to let some other process run. So the idea is switching from one process to another process doesn't happen automatically. Operating system does that, okay? So when the program is done running, it means that either a hardware interrupt occurred or a software interrupt occurred, okay? Before the timer interrupts, or if you don't have a timer interrupt on your machine, that means what? This process one can take the CPU, okay? It can take the CPU. If there are no timer interrupts, it can indefinitely keep using the CPU without giving it away to the other processes. Basically, it runs it and it locks up all the machine. It runs and runs and why does it do that? It is because it's a buggy code, right? Sometimes it does that. But on today's computers, we don't have such a problem. If a program runs in an infinite loop, it will have to be interrupted because a timer interrupt will occur and the CPU will handle it. Okay? It looks like I am way out of time. Let me take some break. Let's be here around 11:47. Please open the windows. Who didn't sign this sheet?
Proje için. O zamandan beri benden. Bana getirin demiştin.
Geçen sene aldın, yeni getiriyorsun.
Pandemiden dolayı hiç okula gelmedim.
Haber ver ya. İyi, tamam. En azından getir.
Ben ders kaydını yeni yapmış, bu listede yok. Ne yapalım?
Hangi listede yoksun?
Bu listede yok.
Sen kimsin ki? Yüksek lisans öğrencisi misin?
Bilimsel hazırlık öğrencisi.
Videoları izlesene. Bu listede insanlar kendileri yazıyorlar bunları. Sen bir videoları izle ya. Dönemin 1/3'ünü atlattın ben. Ne yapıyorsun sen ya?
Nereye imza atacağım hocam?
Derse katılmak için oraya giriş yapmak zorundayız değil mi? Yani yüz yüze derse ben giriş yapamadım, geldim ama sorun olmuyor.
Evet,
sanırım.
sorun olur tabii ki. Yok yazıldınız o gün.
Ha yok. Tamam, o açıdan değil yani. İzin veriyorsunuz yani derse katılmanıza, illa oradan şey olmaz.
Vallahi yok, çok kalabalık olmadığı sürece olur, problem yok. Çocuklar var mı? Ben videoları izle. 6 tane video var, hepsi de bahsettim.
Herhalde evet. Buyur abi. Tamam, sen dersteyken aradın ya, sana dönüş yapayım dedim. Ha, onun için aradın ha, tamam. Tamam. Ya planladık da şu seramiği çatlamışsın.
Hayır, o yüzden almadım. Öyle bir kere. Dersim var. Sonra dersim var.
Şey düşünüyorum da hani değerlendiriyorlar mesela. Yani işte arasında işte kullanmaya devam ediyor. İşte bundan ben de korkuyorum. Şeyimiz kendisi değiştiriyor, batarya değil mi? Kendisi
Sana uyuyor. Valla ben gerçek var ya benim olmaz.
İşte ben de şey yapayım.
Bu hafta kaybettim. Soğuk var.
Kadıköy'de CSE iletişim var. Orijinal takıyorum diyorlar da.
Evet, ben alacağım sana. Alamam.
KVK
Ben de sağlıkta böyle bir kahve alacağım. Soğuk var. Sen nasıl olur?
Samsung'da şey böyle. Samsung şeydi kanka. Bende bir telefon vardı. 800 liralık telefon. Batarya değişimi 400 liraya satmışlar. Telefonun içine bir sürü bileşen var. Sadece batarya mı çok? Yarısı fiyatı.
Ne?
Şeyler gibi ya. İşte iPhone 5s'ler gibi.
Aynen öyle işte.
Bilgisayar var. Adam iPhone'a bile yan sanayi batarya takıyor bence ya. Şey yaparsın, telefonu ben gözden çıkardım dersin. Ben kaç kere Ülken ben de geldim. Ben var ya eskiden çok aptalmışım ya. Ben şey kanka yurtta kalırken telefon düşmüş diye telefonu yaptım. Yani ezilirsen maşallah. İyi.
Orijinal mi satacaksın? Orijinal ne kadar?
Ben hiç öyle su isteği yazmıyordum, mail yazmıyordum. Böyle 5 dakika bekledim, ucundan yazmaya devam edeceğim. Ben cumartesi baktım, akşama doğru yoktu. Ben güzel akşamı baksana 4-8 falan. Yok. O yüzden gidiyorum. Sen bayağı teşekkür hani cana kim geldi, orada bir şey sorun vardı ama bozdu kuruyamadım. Çok memnunum yani. İlk geçen hafta cuma günü akşam oldu. Ben bugün 3 kişi vardı yakaladık karşı. Ama ondan sonra yani. Teşekkür ederim. Finallerde bir hafta. Gerçekten beni
Yine oldu. Başka bir aslında nedenim vardı. O yüzden nerede bakıyorum. Bana bir kod versin. Çevirin artık.
Ben şey için düşünmüştüm. Başka bir motor var.
Mevsimden kaydı ki yani. Bir ay sonra falan ısınır. Aralıkta da yer değişemiyor. Yani. Matem eskiden. Pazartesi de Perşembe baktım ya abi. Perşembe yüzde 90. Bu hafta aslında barajlar falan dolar işte o iyi yandan var işte barajlar var. Yok soğuğunu sağlayıp zaman kalkıyor.
İçiyorlar ya. Biraz öyle. Biraz öğrenciyle oynuyorlar. O kadar değil.
Haftaya ödevi yazacak. Keşke sistem ödevleri yazsın.
Benim bütün derslerim 3'ten kaldı. 4 sekiz
Tek başına yaptığında bir şey yapamıyorsun öyle. Ben ilk defa yaptım.
o sürede
Geçen sene arm vermiştik. Şimdi arm işlem, arm üzerine gidecekmiş. Raspberry Pi backbone falan yapacakmış. Kimse kullanmıyor. X86'ydı abi. Arm yükseliyor yani. Nvidia üretecek. Kaçıncı derece çıkmışlar? Sistem çok zorlaştı. Sistemde 6 tane bize bütün konu değil. Sistem ülkede çok güzel. Ya o şey de bayağı bir iki öyle mi?
Gebze de sinyal çok yüksek. Yani benim ikincide de bir bug vardı. Böyle %1 ihtimali çıkıyordu. Tam segmentation. Böyle 100 defa çalıştırıyorum. Anca çıkıyor. Çözemedim. Zaten çözemedim zaten. Ondan sonra istedim. Yani inşallah hoca söylediği zaman segmentation vermez dedim. İyi de vermemiş. İyi yapmış.
Okay, so this is the main idea of switching between processes. As I said before many times, OS makes this decision who is going to run next, and for the OS to make that decision, OS has to run between the processes. Okay, in reality, this is what happens if you have 4 processes, okay. You run some process A, then some B, then some C, then some D, and it looks like they are all running in parallel. It looks like they are running like this, A, B, C, D. They are running in parallel, but in fact they are not. And this is our assumption in this chapter. We will assume that there is only one CPU available, and you do this time multiplexing to switch from one process to another process, and do it in reality, but make it look like this is happening for the programmers, for the end users. Okay, so how about the process creation? When is a process created? Who creates it? Let's look at those. Of course, at the beginning, a main process has to be created, system initialization time. During the system initialization time, there are many processes created. Some processes are responsible for printing, the other are responsible for web page servers. Some of them are responsible for processing the email and etc. They are usually called our daemons. Okay. When you have the daemons, they just usually sleep. Whenever we need them, they wake up and they handle it. Okay. So they most of the time they are suspended, they are blocked, they are waiting somewhere for something to happen. So who is going to let them that something will ever happen? Of course, it is the operating system. For example, let's say a print server. Okay, what does a print server do? It takes jobs from the processes, okay, and it prints them to the printer. Okay, 2 things can happen. Operating system can say that a new job is available, just print this. The other thing is that operating system might say that the print is available, the printer is available, you can use the printer. Okay, so in both cases operating system will know. Why? Because a process will tell the operating system that I'm going to print this file. Okay, operating system knows it, so it can wake up this printing daemon, or the printer can cause a interrupt, says that I am ready to print one more character, if it's a real old printer. Okay, and operating system will tell the printing server that okay, you can send one more character to this printer. So it is always the task of the operating system to wake up these daemons when the time comes. Okay. So at the initial time, these kind of processes are created. They are initialized. Okay. Execution of a process creation system call, for example, fork for Unix. If I make the system call fork, okay, it will make this new process, which is exactly the same as the other process, calling process. Okay, that's the execution. The other one might be, well, these two are related. From the shell, I say that I like to run this program ls, right? A user request to create a new process. Or sometimes for the batch system, it's a special way of creating a batch. But most of our systems, okay, for the Unix type operating systems or Windows type operating system, there is usually one method to make a new process. It is fork for the Windows Unix operating system, create process for the Windows operating system. Okay, after fork, you just don't do fork. After fork in Unix, you run exec with environment variables, execution with environment variables, or similar system procedures to change your core to the desired program. Or Windows does that, both of them automatically. It makes a new process and it runs the desired program with that process. Okay, the book says Windows has about 100 other functions for managing and synchronizing processes and related topics. POSIX has total of 100 procedure calls. Windows has many more. Okay. Good. And how about this is the process creation. How about the process termination? What kind of process termination alternatives do we have? A process might say that, okay, I am done, everything is fine, I am terminating. So you call exit, okay? Exit system call, exit process for Windows. So voluntarily, sometimes you will say that I cannot continue, I am going to exit. So there is a problem. What is the problem? I cannot open this file, okay? So I am exiting it, I know that I am exiting it, but I am involuntarily exiting, terminating my program. So both of them are done by the process itself. But then there is another involuntarily exiting of your program. You try to access an illegal memory location, the memory location that doesn't belong to you. You try to, for example, change the page table, okay? That is only privileged CPU mode can do, or you try to divide by 0, that will cause an hardware interrupt, etc. Okay, so those are the fatal errors involuntarily. So the fatal errors, operating system will know that you did something bad by the help of the hardware. Okay, you try to execute an illegal instruction, and CPU realizes that you are in the user mode. You are trying to execute a privileged instruction, okay? So immediately it will cause an interrupt, and an interrupt will be handled by the operating system, okay? So that's how the operating system knows that you are doing something bad. Without the help of the hardware, operating system wouldn't know about it. Okay, another one involuntarily exit is the kill, okay? I am killing another process. If I have the privilege of it, if I am the root, if I am the root user, super user of this computer, I can kill whatever I want, okay? And operating system knows it. Operating system says that, first of all, operating system has privilege to kill everybody. But if the user wants to kill something, operating system makes sure that that user has the privilege to kill anybody that it wants, okay? So operating system has to make sure that all the authorizations are valid. Okay, another topic that is related to the process is the process hierarchies. For some systems like Unix, there is a process hierarchy. There is parent-child relationship between the processes. Do I have an example for that one? Do I have an example? No, I don't have it. Okay, but I think I showed you before in my Linux emulation that when I do this E, yeah, this one says that init, the process init is the parent of all, then bash is the child of it, ps is the child of this bash. Okay, there is always a parent-child relationship between the processes, and usually if you kill the parent process here, okay, that will kill all the children of that process, including this bash and its children too. Okay, so there is this parent-child relationship in Unix, but in Windows we don't have this hierarchy. At least it is not supported by the kernel directly. You can emulate this hierarchy in Windows, but it is not the same as the Unix. I am not saying that one is better than the other one, but this is how they designed it. Yeah.
Erhan just said if parent process dies, initial process adopts the child process.
If the child process dies,
parent process dies. Initial process.
Init process.
Init process
Okay.
adopts them.
Well, it can be programmed. It can be changed. I mean, when you do this, for example, if I kill this 7, it's going to kill all of them because I didn't say that these are detachable. There are ways of saying that, okay, this child can live by its own. And since it is in Unix, everybody has to have a parent other than the init. There are ways of handling those kind of stuff. But by default, if you kill this bash, it is going to kill all of its children. If you didn't give the necessary parameters to make it work otherwise. Okay. In Windows, again, I can have this hierarchy, and I can say that this is the child of that one or that one. I cannot find it there, but it is not directly supported by the kernel of the operating system. As you see, everybody is working using CPU, but let me try to see if I can. No, maybe it is in the details. Yeah, let me try to see if this one has any. Where are the features? I couldn't find it. I mean, it is always so confusing to find something in Windows. But they say that, yeah, it is. No, it is the feature of the program itself. But you can emulate these parent-child children relationship in Windows too, but it is not as explicit as Unix. Okay, let's look at the process. Let's remember the definition of the process. Process is an abstraction of a running program. Okay, since it is different from a program, it's not a program, it is running program. A running program has different states. Okay, let's look at these states. A program might be really running. That means what? It is active. It is using the CPU. It is modifying the registers. It is accessing the memory and etc. Okay, so it is currently active. We assume that we have only one CPU on this machine. Okay, that's what the assumption for this chapter is. Okay, so we said that the process is using the CPU. Good, so it is running. That's one of the states. The other one is, okay, the process is ready, but it is not running. So if the process had the CPU, it can continue. Everything is ready, but it is not running. It is waiting in the ready queue. And the third case is the blocked case. Okay. Even if I had the CPU and everything, I cannot continue because I am waiting something to happen. I am waiting for data from the keyboard. I am waiting for data from the network, or I am sleeping. I am waiting until the time is up. Okay. In that case, I am blocked. So a process, basically, these are the most frequently seen states. There are two more states, but they are kind of extreme cases, or the once in a lifetime cases. I am either running, or I am ready, or I am blocked. Okay. If I am blocked, okay, I am blocked. Nobody can help me. I have to wait. If I am running, I am happy because I am using the CPU. If I am ready, I am not that happy. Why? Because I can run, but somebody else is using the CPU, right? So if your ready queue is full of processes, then somebody may not be that happy because I need the CPU, but I am not using the CPU. Somebody is using those resources. So let's see this. Okay, this is directly from the book. This is from somewhere else. I am going to look at this one because this is more explicit. Okay, but the other figure is valid too. So ready, running, or blocked, waiting in this case. This created and terminated are two more states, but they are kind of obvious. So created, a process is created and terminated. So let's ignore these two for now. Let's look at this one. A process is created. It is admitted to the process table. Now it has its entry in the process table. It defined everything. Okay. A process is not running yet. To move this process from the ready queue, okay, to the running state, the operating system scheduler, okay, has to make a decision that, okay, this process can now use the CPU. It's called a scheduler dispatch. The scheduler dispatches this process, and this process is now running. Okay. So while in the running state, it is happy and then it is running. A few things can happen. One is an interrupt. Okay, an interrupt happens. System interrupt happened. A timer interrupt could be a disk interrupt, a keyboard interrupt, a hardware interrupt. Doesn't matter what it is. So operating system has to handle that interrupt. Okay, so as soon as interrupt happened, this process is in the ready queue again, because this process was happy, it was running, but I had to stop it. So it is in the ready queue, and it will wait there until operating system makes the decision that this process can continue. Okay, after handling the interrupt, or other things can happen. This process might say that I need this data from the disk. Okay, and operating system is going to handle that request. This process will ask the operating system to do that for itself. So that's how you go from the running state to the waiting state, because operating system cannot handle that request immediately, because it takes time to do I/O. I/O is slow. Okay, so I am waiting in the blocked queue. Okay, I am waiting in the blocked queue. So we looked at this connection here, this transition. We looked at this transition and we looked at this transition. Or when I am running as a process, I can say that I can tell the operating system that terminate me. Okay, in that case, operating system is going to terminate myself, and I will be in the terminated state. I am not a running program anymore. Okay, I am not a process anymore. I am just terminated. Let's look at this blocked queue or waiting queue. So how am I gonna move from this state to this state? Well, as you see, there is no arrow between this position to this position, this state to that state. There is simply no. I mean, you cannot go from waiting to running. Okay, first you have to be ready. So who makes you ready? Of course, it is operating system. So I am waiting in the blocked queue. I am waiting for I/O to happen, right? So the disk loaded. I am running first. Let's say I'm running. I need some data from the disk. I ask the operating system to load that data. Okay, and operating system put me in the block queue, and it worked on that data while somebody else is using the CPU. And when the data is ready, the disk causes an interrupt. Okay, this caused the interrupt. Operating system handled that interrupt, and handling of interrupt made that data ready for me. Now operating system knows that my data is ready now, and so it puts me in the ready queue, because all the data that I need is in the required buffer. I am in the ready queue now because I can continue whenever the CPU is available. Okay, so I/O or even completion. Whenever it is done, operating system changes my state. Okay, as a process, I don't know that, because as a process, in fact, when I say read from this file to this buffer, okay, when I execute this command as a process, I don't know that I was blocked. I don't know that I waited in the waiting queue or the block queue, and I don't know that I was available to run to use the CPU for a while in the ready queue. All I know that after this instruction is executed, I have my data inside this buffer. That's what I know. Okay, so operating system handles all kind of stuff about my process. So I am waiting in the ready queue. Whenever the CPU is available for me, again another schedule dispatcher, I keep running. Okay, good. So let's try to. This is not happening. Also, this is not happening either. Can anybody tell me why this is not happening? This cannot happen. Nobody can go from the ready queue to the waiting queue. Yeah?
Because in order to transition to the waiting queue, you have to call a system call. You have to make a system call.
Yeah, exactly. Because I don't know if anybody heard you, but he said that to be able to go into the block queue, okay, as a process you need to make a system call, okay? Do this something for me. If I am in the ready queue, I am not running, right? If I am not running, I cannot ask the operating system to do something for me, okay? If I am ready, I am ready. I cannot be in the block mode while I am not running, okay? So there is no transition from the ready queue to the waiting queue. The only way is to go that way, okay? Only way is to go that way. Good. Also, there is no way to go there either. If the operating system is killing me, okay, if somebody is killing me, they don't directly kill me. They give me a signal saying that we are going to kill you. Do your last things, okay? Remember when I try to shut down this computer, okay, it just doesn't immediately shuts down. Sometimes Word program tells me that this computer is shutting down, but you have unsaved files. You like to save them, right? You just don't immediately kill them. So you put them in the running state again, and you signal them that I am going to kill you, and I am going to handle that signal saying that somebody is going to kill me and I need to do before I die such and such. So there is no transition between ready to terminated either. Okay. Yes.
Some malware softwares, when you close it, it immediately opens new one. So last wish opening new one instead of when they close it.
Well, I mean, they are not. They know that they are dying, but they are not objecting to that I am not going to die or should I do something. When they restarted, they look up whatever they were doing last time. If they properly shut down or somebody killed them, okay, they try to achieve the same state. So usually, for example, in this one, if I modify something like this, this is Edge, right? This is Microsoft's browser. When I try to close it, it says that I cannot close it immediately because there are some modifications on it. Okay? But if I didn't modify anything, it just immediately closes it. But the next time I open it, it's going to tell me, should I restore your pages and etc. So it is up to the program to make that decision. I mean, keep the backup of the data that are not saved, or ask the user if they should discard those stuff. So it is not the operating system's behavior what you are seeing. It is the behavior of that program. Okay, involuntarily exit stuff. Good. So that was it. So the book says it. Let's look at it. Okay, running to block to ready. So one is process blocks for input. Two is scheduler picks another process. It puts me in the ready queue. And three is scheduler picks this process. Block to ready is input becomes available. So these are really basic states of a process. It is important to understand what's going on. Most of the processes that I showed you that are running on my system, they are all blocked actually. But it says in this case it's working, but working in this case means it is ready. It is not using any CPU at all. So the ones that are really running are these. Okay, this one. So if you see a 000 there, it is using the 0% C and it says it's working. It means that it is ready. Actually, it is not working. So most of them are really operating system processes. I don't know what they are actually. Runtime broker and etc. This one is something to do with the networking. Okay, most of them are like, oh, okay, see, this is the Linux stuff. Okay, Windows subsystem Linux, and it says it is working, but in fact I am not doing anything. It is not working. It is just ready. Good. Did I miss anything? Yeah, no. Okay, running, ready, and blocked. Good. So let's look at this scheduler thing again. The scheduler is part of the operating system. Okay, it is responsible for making a decision on who is going to use the CPU next. Okay, at the lowest level of the operating system. That means what? On top of the scheduler, there are other operating system procedures or the layers, but scheduler is usually at the bottom. And if you are doing a microkernel operating system, you cannot leave scheduler out of your kernel to make your kernel smaller. It has to be part of the kernel part of the operating system. Okay. This scheduler, as I said, after each interrupt handling makes a decision: are you going to use the CPU or this one or that one and that one? So scheduler runs an algorithm to make those scheduling decisions. Sometimes those algorithms are very, very simple. They say that, okay, round robin, you just run process number 0, then 1, then 2, then 3, then n-1, then after that go back to the beginning. That's how the scheduling is done. So this is as simple as a circular queue. Okay, if a process is terminated, you take that process out of the queue. Okay, if a process is added, you just add it at the end of the queue, and that's it. So a scheduler might be as simple as a round robin scheduler. Okay. So when you implement a process, what do I mean by implementation of a process? We are not, of course, talking about the implementation of the program. We are talking about the implementation of the process. Remember what the definition of the process again? Process is a running program. Okay, for a running program to go into these states, okay, block state, running state, and ready state, I need to keep some data about each of the processes. Okay, so as we talked about before, we have a table which is called the process table, and every process has an entry in that table. Okay, so for each process I have this kind of information depending on the operating system in my process table. Okay, the information about process management, the information about memory management, information about file management. For example, for the process management, I need to keep copies of my registers when I am waiting in the ready queue or the block queue. By the way, this is block queue, and this is ready queue, but this is not running queue. Okay, this is running because there is no queue here. Okay, a single process can run, can take the CPU. A single process can run, can take the CPU, but many processes could be blocked, many processes could be ready. And I need to have a way of keeping my data while I am in block mode and while I'm in ready mode if I am not using the CPU. When I am using the CPU, my registers are already CPU registers, right? Whatever the CPU holds, those are my values. But if I am not running or if I am blocked, then I need a way of keeping that data, and I keep them in my entry of the process table. My registers, my program counter, my PSW, stack pointer, well, these are all actually registers. My process state, am I ready? Am I blocked? Okay. Am I running? Those are the process states. My priority. There are some processes more important than the other processes, right? For example, some system processes, they have to be run immediately. They have to be quick, so their priorities are high. If I am a backup process, okay, I am taking a backup of the disk, I could be slow, that's okay. I could take overnight to run it, okay? Scheduling parameters. What kind of things? For example, how much time I am allowed to use the CPU, okay? Those are my parameters. My process ID, remember the process IDs? Everybody has an ID, and my init process has ID number 1, the other one is ID number 7. These are the process IDs. Every process has a unique process ID. Parent process, if my operating system supports it. Process group, maybe I belong to a group of processes. My signals, if I am using a Unix-like stuff. Time when process started. This is important. When did I start this process? So that I can know how old it is. Sometimes this is important to know for the scheduling task. CPU time used. I might be an old process, but maybe I didn't use that much CPU. Okay. I am responsible for all these child processes. How much time did they use? And time of next alarm. These are alarm is the timer. Remember this one. When I say sleep 100, okay, I am setting up the alarm, the timer, and process table. I am blocked, and I keep that data inside this process table. So these are process management related stuff. Some memory management related stuff. I know that each process should keep some data in memory, but where is that data? Okay, so my pointer to the data segment, stack segment, text segment, and etc. They all have to be kept in my process table. And file management related stuff. For example, my working directory, my user ID, my group ID, so that I can adjust my privileges and etc. So all those kind of information. Well, this is not an exhaustive list. Again, depending on the operating system, some of them are missing, some of them are not here. So these are some typical process table entries, and I keep this data for each process, and I have to keep this table in my memory, and that memory has to be protected because only the operating system can see this memory. Right? Only the operating system can access this memory directly. So that's the process table, an array of structure. Yes.
What was the priority?
What was the
priority entry here? Right. Priority entry.
Priorities again. I mean, processes has priorities depending on what they do. As I said, some processes, for interactive processes, you have set a high priority because if I am using this computer, I want it to be interactive. Whenever I click something, I need immediate answer. Okay, that process has to be given more priority. When I am scheduling it, okay, if that process is ready, then it should run. But if I am a backup process, I am taking a backup of 2 terabyte disk. Okay, I know that it's going to take 2 hours, and there is no hurry for it. As long as it is done in a few hours, I am okay. So maybe the backup process's priority shouldn't be that high. Interactivity is more important. Okay, or handling of the interrupts has the highest priority, because if I don't handle the interrupt that comes from the network card, maybe I'm going to lose that data. Okay, so again, priorities are defined by the operating system, and sometimes you define your priority yourself. Nice is a program in Unix to lower your priority. For example, when you say nice ls, run ls in a lower priority mode. So you become a nice process. When you say nice and nice ls, so run nice ls in nice mode, so it is even nicer. Okay, but I forgot the parameter for nice. You might prefer the other way of, okay, command. I think there is a, can I make it unnice, renice? So there is a way of specifying how much niceness you like to impose. Okay, from 20 to 19. Okay, so minus 20 is okay. This is the niceness, negative niceness. You can be negative nice 20. That means that I like to increase my priority, but to specify a negative niceness, okay, you need to be a root or something like that. Can I do that? Nice minus 10 ls. Well, I couldn't find it. So you can specify it, but it will ask you the root password. You cannot increase your priority by yourself, but you can decrease. If you like to be nice, then just okay, be nice. Okay? So sometimes you can change your priority, but most of the time it is the task of the operating system. I guess I am out of time. I will stop at this point. Okay, thank you. I will see you next week.